Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, I'm Indah Kartika from University of Lampung. I made this video about are the natural indicator to detect the presence of hazardous metals in the environment. How does it work? I made this video with the title Most as a bioindicator of heavy metal pollution in the environment. Some environmental pollution comes from nature and most of it comes from human activities, transportation activities, mining, agriculture, industry and factories, and others. One of the impact of transportation activities is the occurrence of air pollution, namely the occurrence of exhaust gas emission. Lead, Pb, is a heavy metal that is toxic, which has an impact on the environment and human health. This graph contains data of national emission reported to the Convention on Long-Range Transboundary Air Pollution provided by European Environment Agency. From this graphic, we can see that cadmium is still high in Iceland, Turkey and Liechtenstein, increasing by 200% while Lithuania has increased slightly. In addition to lead and cadmium, heavy metals such as mercury, arsenic and iron can have a great effect when they enter the body. Heavy metal is one of the toxic pollutants that can cause death and non-death such as impaired growth, behavior, and morphological characteristics of various organisms. To avoid the danger it causes, indicators are needed to find out whether an environment is polluted by hazardous metals as described earlier. Natural indicators that can be used to detect the presence of hazardous metal in the environment include spider web and lichen, and then honeybees and their product. Mosses as a bioindicator. One of them is Leptodictyum riparium. From the explanation above, we know that one of the bioindicators used to detect heavy metal in the environment is moss. According to Grondel, Stutler, and Bartholomew Began, mosses are perennial plants that are evergreen, having filament-like roots that only anchor them to their substrate, i.e. tree bark, soil, rock, or sand. They rely heavily on atmospheric deposition to meet their micronutrient requirements due to their pseudo-root system. Mosses have a relatively high surface-to-volume ratio compared to taller plants. They grow in colonies, forming dense green clumps or carpet, thus absorbing nutrients from the atmosphere maximally above their physiological requirements. LeBlanc and Rowe, 1974. The above characteristics are also evidenced by the presence of a thin layer of cuticle above the epidermis, which makes the tissue easily permeable to water, gases, pollutant, and some metal ion. The advantages of moss as a bioindicator include cheapest, available in nature in large quantities, the simplest for reliable atmospheric monitoring, and non-toxic. In a study conducted by Bargali, he concluded that moss and lichen are dominant vegetation under extreme alpine and polar conditions and are widespread throughout the world. Several research articles reported the use of different lichen species as bioindicator as well as monitoring agent for quantitative assessment of metal deposition in the environment. Some of the popular species used by various scientists are as follows. Research in the urban part of the city of Loja and the surrounding forest conducted by Angel Bennett in 2019 showed result as shown in figure 2. Let's focus on the data market. In Parma-Trema Arnoldi, CD level range from 0.6 mg per gram forest to 34.7 mg per gram in central. The result of the LMM so that the concentration of heavy metal in Parmotrema arnoldi and Tillandsia usnades were significantly different in the fourth zone. This indicates that the concentration of heavy metals in Parmotrema arnoldi, lichen, and Tillandsia usnades reflects the deposition of heavy metal in the city of Loja. Furthermore, from the journal written by Nikita Yusin et al. In 2020, they conducted a biomonitoring study conducted in the Moscow region in 2019 and 2020 compared. Lichen sampling has proven to be a suitable and low-cost indicator of heavy metal air pollution. 8 elements were determined in lichen samples analyzed using atomic absorption spectrometry. The results are present in Table 1. The CV values for all elements in both years were less than 75%, which point to the main influence of the regional source of pollution. The higher values of the mean PB content in 2019 until 2020 in comparison with 2014, this is because the most samples were collected at different sampling sites. In 2014 in the northeastern part of Moscow, whereas in 2019 until 2020 in places considered to be potentially highly polluted, the iron content was the highest in 2014. Heavy metals get deposited on cell surface layer by dry deposition, may reach to cytoplasm through intracellular uptake and extracellular uptake. Intracellular uptake includes diffusion and transport of heavy metal also occur through leaf and rhizoid, along with water and micronutrients. Then extracellular uptake including ion exchange process and chelation. The most probable and accurate mechanism of heavy metal accumulation is the cation exchange capacity or CAC of most cell wall. CAC is the maximum number of cation exchange with anion in the cell wall per gram dry weight of the tissue. This is the number of protons that bind to the tissue in a form that can be exchanged for metal ion. The cell wall network serves as a strong ion exchanger because the network contains high polygalacturonic acid and has many functional groups such as phosphodiester, amine, and sulfhydryl, and the most dominant negatively charged metal binding groups such as carboxyl and phosphoryl group, which act as dynamic cation metal ion exchange. See Figure 2. Thus, metal ions are immobilized by the negative charge of the cell wall. The stability of metal organic complexes, chelates, and large ion exchange capacity of most tissue make it a good absorber as well as a heavy metal absorber. Gonzalez et al. 2016 experimentally observed through X-ray absorption spectroscopy that Q was significantly adsorbed onto cellulose present on the cell membrane surface of the Pseudoscleropodium purum, Hypnum sp, Sphagnum dentaculum, and Bracteoseum rutubulum species. Cellular localization of CD, Cu, Pb, and zinc performed by X-ray TEM microanalysis showed metal peaks in cytoplasmic, vesicle, and within the cell wall.